Here we have steam, which is the working fluid in this ideal regenerative Rankine cycle. Okay, and it has one closed feed water heater. Okay, so that's the schematic that's shown here. Now, superheated vapor, it enters the turbine at 12 megapascal. 12 megapascal is basically 120 bar and 440 degrees Celsius. Okay, so we know exactly the state for the state one. We know the temperature and the pressure. We can fix it. The condenser pressure is 8 kilopascal. All right, so that's the pressure here. It's pretty low. It's lower than the atmospheric pressure. Okay, now steam expands through the first stage turbine, where some of it is extracted and diverted to the closed feed water heater, which is operating at 0.5 MPa. Okay, so as expected, some part of the steam expands. The steam expands and some part of it is extracted to be sent to the feed water heater, and the rest continues to expand within the second stage of the turbine, right? And this extraction is occurring at 0.5 megapascal or 5 bar. Okay, this is where you're extracting it. So as we have seen before, this pressure is somewhere between the boiler pressure, which is 12 bar, and the condenser pressure, which is 0.08 bar. Okay, so somewhere between these two. All right. So what else is given? The condensate drains from the feed water heater as saturated liquid at 0.5 megapascal and is trapped into a condenser. Okay, so what it's saying is that the condensate that comes out from this, the hot fluid that comes out from this closed feed water heater, is basically saturated liquid. So we're talking about state 7. So we're saying it's saturated liquid, that is x is equal to 0 for it, and it's coming out, of course, at the same pressure, 5 bar, and we then trap it into the condenser. Trap it into the condenser simply means that we send it through a trap and then from there to the condenser. So what's happening in the trap? Well, it's simply isenthalpic expansion. So H7 is going to be equal to H8. All right. So a constant enthalpy expansion. So it's going from a certain pressure of 5 bar here to a pressure of 0.08 bar at state 8. That's all what's happening, expansion. Then what else is given? The feed water, it leaves the heater at 12 megapascal. So 12 megapascal is the pressure of the boiler, and that's the pressure state 5 is at and state 6 is at, right? So the feed water, it leaves the boiler at this pressure at 12 MPa or 120 bar, and a temperature which is equal to the saturation temperature at 0.5 MPa. So now we're telling you the temperature at state 6, right? We're saying temperature at state 6 is equal to the Tsat at 0.5 MPa or Tsat at 5 bar. Okay, so this is given. So basically the temperature at T6 is equal to the temperature at T7, because T7 is also at that pressure and it's actually the saturated liquid. So this is all what we know. This is the information that has been provided to us. Now, based on this information, we need to do a couple of things. We need to first show the cycle on the TS diagram. Okay, so you should know how to draw the TS diagram. We have to calculate the rate of heat transfers, two rate of heat transfers, which we'll talk what each one of them is, and also the thermal efficiency. So let's go ahead and first look at this TS diagram and look at how we can get the enthalpies at different states. As you know, if you want to determine heat QN, heat rejected or heat input to the system, or even the work output of the system, for any of those things, you're going to need the enthalpies, right? So first task is to get the enthalpies. Okay, so for getting the enthalpies, a good practice is to draw the TS diagram if you don't have it already. Okay, so this is the TS diagram that's drawn here. It's indicating the, let me use a different ink. It's indicating the boiler pressure of 120 bar, indicating the feed water heater pressure, or the pressure from the hot fluid of the feed water heater at 5 bar, and the condenser pressure of 0.08 bar. Now this is very similar. This is exactly, I mean, the same TS diagram that we have looked at when we were discussing the closed feed water heater, right? So you have something at state 1 expands till state 2, and at state 2, right, which is we extract some steam and send it to the feed water. The rest continues to expand within the turbine, reaches state 3, okay, and then at stage 3 we send it to the condenser like we show here. And what we do with the other hot fluid is that the hot fluid that we extracted at stage 2, we send it to the feed water heater. It comes out at stage 7 with a saturated liquid as given in the question. Then we send it through a trap, okay. In a trap, it basically undergoes expansion, so goes down from 5 bar to 0.08 bar while maintaining the enthalpy, right? So H7 remains equal to H8, and at state 8, well, it's somewhere here, it's a mixture. They both combine, and what we get at state 4 is saturated liquid. Okay, so state 4 is basically saturated liquid as always, and at the condenser pressure. Now 4 to 5, we pump it to the boiler pressure directly. So we are pumping it from 0.08 bar to 120 bar. And at state 5, right, it enters this feed water heater. This is the cold liquid. It needs to get heated. Okay. Here, the thing that we need to define is state 6. So state 6, it's at the same pressure as state 5. P5 is equal to P6 is actually equal to P1. So that's the boiler pressure. So we need one more thing to locate the state 6, and we have been provided the temperature at state 6. And the temperature we said is equal to Tsat at 5 bar, okay, which is this pressure right here. So when you draw a TS diagram, the temperature for state 6 should be equal to the temperature of state 7, because state 7 is at the saturation temperature at 5 bar. All right. So now that we have drawn the TS diagram, let's look at how we can determine the different properties. Any questions with the TS diagram, or any question with whatever we have covered till now? All right, no questions. Okay. So let's start with state 1. So well, okay, before I start and show these different properties, the reason I'm doing this is because when we ask such a question in the exam, in the class test or in the exam, we're not going to give you all the properties. Okay, we're going to give you some properties or some enthalpies, and some you need to determine. So obviously I'll give a mixture, or we tend to give a mixture of some easy and some difficult ones, right? So, or some requiring more effort, let's say. Not the difficult probably is not the right word. So you need to know how to determine the enthalpy of each state. Okay, so I'm going to walk through it rather quickly here because we have done this several times, but I'll focus more on the things which are new here. Okay, and so please make sure you understand this part as well. So if when there's a need, you should be able to solve for it. All right, so let's look at state 1. Okay, we start from state 1. At state 1, the pressure and the temperature was directly given. So it's simply a matter of going to the tables and picking up the value of enthalpy. We also get the entropy simply because we know that the process 1 to 2 is an isentropic expansion. So S1 is equal to S2. Okay. And we know the pressure at state 2. It's 5 bar. So using this 2 information, we are able to locate state 2. We determine the mixture quality at state 2. And we use that to determine enthalpy. How do we determine X2? Well, we make use of the fact that we know the entropy at state 2, and we know the values of SF and SG at 5 bar, okay, which we get from the table. So that's how we get it. We have done this several times before, so you know exactly how to do it. Okay. Now for state 3, well, again, the entropy at state 2 is equal to entropy at state 3, right? 2 to 3 is again an isentropic expansion. So we again have to do exactly the same situation. We go and determine the mixture quality at 0.08 bar and use that to determine the enthalpy. Okay, so 1, 2, 3, we already got the enthalpies. Now state 4 is very simple because state 4 is simply saturated liquid, right? At the condenser pressure. So We know the condenser pressure, we know the quality is 0, so you just pick up HF, right? That's all it is. Now we have got state 4. Now the thing is, how do we get state 5? Well, the way to get state 5 is just like the way we have been doing till now, in part 1 as well, right? So we make use of the reversible work input formula, which is simply specific volume times the pressure difference. Now, specific volume is something that we can calculate very easily because it's VF, right, at condenser pressure, 0.08 bar here, and P5 and P4 are given in the question, right? So this is the P5 is the boiler pressure, P4 is the condenser pressure. So it's simply a matter of plugging in the numbers and making sure the units are consistent. And once you do that, you get the enthalpy H5 as 185.97 kilojoule per kilogram. Okay, so make sure you're picking up the specific volume correctly. So P5 is also, the way we determine P5 is very similar to what we have been doing till now. Now the interesting part is state 6. So for state 6, we know the pressure. Okay, this is one property known. The other property, as I said, is its temperature. And we said it's Tsat at 5 bar, right? So that's 151.86 degrees Celsius. Now, state 6 is compressed liquid. Okay, for compressed liquid, we said that the enthalpy and other properties such as internal energy and entropy, they depend only on temperature, right? They're not a very strong function of pressure. So what we can do is we need to get the HF at the same temperature. So HF at temperature 151.86 is basically the HF at 5 bar, right? Because that's the Tsat at 5 bar. So the HF at this temperature is 640.23. Okay, so this is what we again get from the saturated tables. You go to the pressure table, pick up 5 bar, and this is the Tsat there. So this is the temperature that defines state 6. And again, this is simply the enthalpy that you get from there. So remember, state 6 and state 7 are exactly at the same temperature, okay? And state 7 is simply saturated liquid there. It's simply HF at 5 bar. So of course, the enthalpy at state 6 will be equal to the enthalpy at state 7. And that's only the case because T6 is equal to Tsat at 5 bar. If T6 was something else, then these two will not be the same. Now, once you have state 6 obtained, and once you have enthalpy at state 7 also obtained, determining enthalpy at state 8 is very simple, right? We told you that in a trap, isenthalpic expansion is happening, so H7 is always equal to H8 if you have when you're dealing with a trap, or the enthalpy at inlet and the exit of the trap is exactly the same because that's the way it is designed. So H8 also comes out to be 640. So this is what we have determined, and this is how you determine the different enthalpies or enthalpies at all the states that you need. Okay, once we have this information, we can go ahead and start solving the problem. So now let's look at the first part. In the first part here, we need to determine the rate of heat transfer to the working fluid that's passing through the steam generator. So this is the steam generator right here. Okay, we need to determine this rate of heat transfer in kilojoule per kilogram of the steam entering the first stage of the turbine. So the mass flow rate of steam entering the first stage of the turbine is m.1, and the heat that is transferred to the working fluid is steam, right? The heat that's transferred to the working fluid in the steam generator is basically Qn. Okay, so we simply need to determine what is how much is Q dot n by m.1. Okay, this is all what we want. We don't want Qn only, we want Qn by m.1. Okay, so it's simply a matter of applying energy balance on this steam generator, and as we have discussed several times before, so it's simply H1 minus H6, right? So we have these enthalpies directly from the table that we determined just now. You plug in the numbers and you get the quantity here. Again, if this is something that we discussed before, but if you're not clear about it, you can talk to me later. But this is something that simply comes from applying energy balance to the steam generator. Okay. Now let's look at the other part, the thermal efficiency. All right. So when we are calculating thermal efficiency, it's simply the network output by the heat input. Okay. Or I could just write it as network output per unit mass by Qn per unit mass. Okay, so now let's figure out how we can get this net work output. Here the network output is basically the work output in the first stage of the turbine, right, plus the work output in the second stage of the turbine, minus the work input in the pump. All right, so it's mass flow rate, which is m dot 1, times the enthalpy change within the first stage turbine. So that's H1 minus H2 plus, now is the important part, the mass flow rate for the second stage turbine. For the second stage, only 1 minus y is expanding, right? So 1 minus y times m dot 1 times H2 minus H3. Okay, so this is the entire work output from the turbine minus the work input to the pump. Now at stage 4, we said everything had joined together, the two fractions, y and 1 minus y. So we are having m dot 1. So minus m dot 1 times h5 minus h4. All right. So net work output by m dot 1 simply equal to h1 minus h2 plus h2 minus h3 minus h5 minus h4. Okay. Sorry, 1 minus y times, I missed the 1 minus y here. All right, so this is the important part. Now for when we look at this, we have all the enthalpies given, right? The only thing we don't know here is y, and that's something that we need to determine. So you got to be careful when you're writing the work output for a turbine where you have a closed feed water heater or an open feed water heater. It is not equal to H1 minus H3. This is completely incorrect. You have to sort of break it down into two because the mass flow rates are different in each state of the turbine. Okay. Now the question is why, right? The fraction y that ends up that goes to the condenser, and 1 minus y is something that we need to calculate because that's what's expanding in the second stage of the turbine. So how do we find the value of y? How do we determine this y?
Maybe taking our system as the closed feed water heater and do the energy balance maybe to find mtot.
Exactly. That's all you need to do. You just need to apply energy balance to the closed feed water heater. So we just discussed how to apply energy balance to the closed feed water heater. You just have to take care of the two inputs here, right? One is the hot fluid coming on with y times m dot 1 and the cold fluid coming with m dot 1 times h5 and going out at two different enthalpies with the same mass flow rates at which they came in, right? So be sure that the y for a closed feed water heater in this configuration comes out to be this equation. So it's the enthalpy increase of the cold fluid divided by the enthalpy decrease of the hot fluid. So when you plug in the numbers, you get this fraction, 0.243. So 24.3% of the steam that entered here, right, that entered as state 1, is extracted and sent to the feed water heater. The remaining 76% approximately continues to expand within the turbine, and then it sent to the condenser. Okay, so this is all what was happening there. Now we can plug in the numbers right here. Okay, into we have everything. We have all other enthalpies. We just need to plug in the number for y, and once you plug it in, you get the network output per unit mass again, which is 1075, and we can use that to calculate the thermal efficiency, right? So we just have the work output per unit mass and then heat input per unit mass. You substitute the numbers, and this is what you get. So it's certainly higher than the case where you don't have a feed water heater, right? Without feed water heater, the efficiency would probably be around 38%. Okay, so this is part B. Now let's look at part C. In part C, what we're asking is we need to calculate the rate of heat transfer from the working fluid, from the water or the steam that's passing through the condenser to the cooling water in kilojoule per kilogram of steam entering the first stage of the turbine. So there is some amount of heat being rejected or transferred from this condenser or the working fluid to some cool water. We don't know what that cool water is, but we need to just calculate how much heat is being rejected in the condenser. But we need to calculate Q dot out per unit mass of the steam entering the first stage. So we're talking about Q dot out by m dot 1. Now, how do we do this? Well, again, by simply applying energy balance on the condenser. Now, for the condenser, we got to be careful. Okay, it has two inlets and one output. Now, it has one inlet coming with a mass flow rate of 1 minus y times m dot 1. It's coming in at state 3, so S3. The other inlet, which students tend to miss, is this other thing coming from the bottom. It's coming with a mass flow rate of y times m dot 1 and at state 8, so it's H8. On the other side, what's going out is heat being rejected. This is one way of energy transfer. The other way is basically through the mass that comes out. So of course it comes out as m dot 1 times H4. Okay, so this is what's coming in here. We have everything known, all the enthalpy is known, y also known. We can plug in here and get this equation. Okay, this is the value for Q out. Now, if you wanted to calculate the thermal efficiency, you could also calculate Qn and Q out, and then calculate the thermal efficiency using this formula right here, 1 minus Q out by Qn, instead of calculating the network output. Or if you are not comfortable with doing the energy balance in the condenser, you could make use of the thermal efficiency and Qn as you calculated in part A and part B to go ahead and calculate Q out using these values. It just depends on how you want to do it. Okay, so that's the end of the class. If you have any questions, let me know. Otherwise, we meet on Thursday.
Doctor,
Yes, go ahead.